Welcome back. Last episode, we projected vectors onto subspaces and found that everything is cleanest when the basis is orthonormal, perpendicular directions, each of unit length. Today we answer the obvious follow-up question: what if our basis isn't orthonormal? The vectors we're handed, the columns of a real data matrix, point in all sorts of crooked directions. We need a way to straighten them. That machine is the Gram-Schmidt process. It takes any basis and grinds out an orthonormal basis spanning exactly the same space. The engine inside each step is the projection we built last time, and once we run the process carefully and keep the books, something lovely falls out for free: a factorization of our matrix as Q times R, where Q has orthonormal columns and R is upper triangular. That QR factorization is one of the workhorses of numerical linear algebra. Let's see why orthonormal is worth all this effort, then build the machine. First, the motivation. Why chase orthonormal bases at all? Because they turn hard operations into trivial ones. Take any vector v. If your basis is orthonormal, the coordinate of v along each basis direction is just v dotted with that direction. No system of equations to solve. One dot product per coordinate. Projection gets equally cheap. To project v onto the span of the first few basis vectors, you simply add up those dot product pieces. Compare that to last episode, where a general basis forced us to invert A transpose A. With orthonormal columns, there is nothing to invert. And the matrix made from orthonormal columns, call it Q, barely distorts space at all. Q transpose Q is the identity, and multiplying by Q preserves every length and every angle. A square matrix like that is called orthogonal, and geometrically it is a rigid motion, a rotation or reflection, so orthonormal bases are worth real effort, and Gram-Schmidt is how we earn them. Here is the process itself. We're handed independent vectors a1 through an, and we want orthonormal q1 through qn spanning the same space. Step 1 is the easy one. Take the first vector as is, and just normalize it to unit length. Divide by its own magnitude. That's q1. Step 2 is the heart of the method. Take the second vector, a2, and subtract off the part of it that points along q1. That part is the projection of a2 onto q1, which is a, 2 dotted with q1 times q1. What remains, call it v2, has had all of its q1 components stripped away so it is perpendicular to q1. Normalize it to get q2. The general step k just repeats this against everything chosen so far. Take ak, subtract its projection onto each earlier q, and you're left with the piece pointing in a genuinely new direction. Normalize and move on. Each leftover is exactly a projection error, which is why it comes out perpendicular. It's worth pausing to see that Gram-Schmidt is not a new idea. It's last episode's idea applied over and over. Recall that when you project a vector onto a subspace, the leftover error is automatically perpendicular to that subspace. That's precisely what each Gram-Schmidt step does. At step k, the span of the directions you've already chosen is a subspace. You project the new vector ak onto that subspace and you keep the error, the part that the existing directions could not produce. By the projection theorem from last time, that error is guaranteed perpendicular to the whole subspace, hence to every earlier q. So the entire process is just project, keep the error, normalize, project, keep the error, normalize. Each step peels off a fresh perpendicular direction. If you ever get an error of 0, it means ak was already in the span. The vectors were dependent. For an independent set, every error is non-zero and you get a full orthonormal basis. Now for the payoff. As we ran the process, we were quietly computing a lot of dot products, how much of each original vector pointed along each new direction. Let's not throw those away. Rewrite each original vector ak as a combination of the q's. The crucial observation is that ak only involves q's with index up to k. It never needs a direction discovered later, because those didn't exist yet when we built ak. That only earlier and current pattern is exactly what makes a matrix upper triangular. So if we put the original vectors as columns of A, the orthonormal directions as columns of Q, and all those dot products into a matrix R, we get A equals Q times R. Q has orthonormal columns. R is upper triangular because every entry below the diagonal corresponds to a later Q appearing in an earlier A, which never happens. R is simply Q transpose times A. The factorization drops out of honest bookkeeping. Let's record what Q and R guarantee. Q has orthonormal columns, so Q transpose times Q is the identity. When A is square and invertible, Q is a true orthogonal matrix, meaning its transpose is its inverse. That's as nice as a matrix gets. R is upper triangular, and its diagonal entries are the lengths of those leftover vectors, the magnitudes of vk, which are all positive for an independent set, so R is invertible. Why does this matter in practice? Because it makes solving systems painless. To solve AX equals B, substitute QR for A, multiply both sides by Q transpose, and since Q transpose Q is the identity, you're left with Rx equals Q transpose B. And R being triangular means you finish by simple back. Substitution, no elimination needed. The same trick handles least squares next episode. And iterating the factorization, swapping QR into RQ over and over, is the famous QR algorithm that numerically computes eigenvalues. One factorization, many jobs. A quick but practical distinction. When A is tall, more rows than columns, there are two versions of QR. The one Gram-Schmidt naturally produces is the reduced or thin version. Q is the same tall shape as A, with one orthonormal column per original column, and R is a small square upper triangular matrix. That's usually all you need. But sometimes you want a full QR, where Q is a complete square orthogonal matrix. To build it, you keep going past the columns of A and add orthonormal vectors that span the orthogonal complement of the column space, the directions A never reaches. Then Q is square, and R picks up extra rows of zeros at the bottom to keep the shapes matching. The two carry the same information, the full version just pads things out. For solving least squares next episode, the reduced version is all we'll need, but it's worth knowing the full one exists, because theoretical results often state it that way. One honest caution about doing this on a real computer. The version we wrote down is called classical Gram-Schmidt. For each vector, you subtract all of its projections onto the earlier directions in one shot. On paper, that's exact. But in finite precision arithmetic, tiny rounding errors accumulate, and the Q vectors slowly drift away from being truly perpendicular. The fix is a rearrangement called modified Gram-Schmidt, where you subtract one projection at a time and update the vector after each subtraction. It's mathematically identical, same answer in exact arithmetic, but numerically much more stable, because each step works with an already cleaned vector. In practice, the most robust solvers don't even use Gram-Schmidt, they use householder reflections, a different route to the same QR factorization. The lesson generalizes well beyond this episode. The cleanest formula for a concept and the most reliable algorithm for computing it are sometimes two different things. Here is the one Gram-Schmidt step drawn out. The navy arrow A1 points off to the right. We normalize it to the short green unit arrow Q1 along the same line. Now the second navy arrow, A2, points up and to the right, leaning away from A1. To orthogonalize it, we find its shadow along Q1, the gold arrow lying flat along the Q1 direction, which is A2 dotted with Q1 times Q1. Then we subtract that shadow from A2. The orange arrow, running from the tip of the gold projection up to the tip of A2, is what's left, V2. Look at the little red square. V2 stands perpendicular to Q1, exactly because we removed every bit of A2 that pointed along Q1. Normalize V2 to unit length and you have Q2, the second orthonormal direction. That single picture, repeated against all earlier directions, is the entire process. Subtract the shadow, keep the perpendicular remainder, normalize. This figure shows the factorization as a whole. On the far left is our matrix A, drawn as three crooked navy columns crammed together, the original basis, pointing every which way. The equation says A equals Q times R. The middle matrix, Q, is drawn as three clean green columns, mutually perpendicular and each of unit length, the orthonormal basis Gram-Schmidt produced. The right matrix, R, is small and square, shaded gold on and above its diagonal with zeros below, upper triangular. Read it this way. The messy columns of A are reconstructed by taking the tidy orthonormal directions in Q and mixing and scaling them according to the triangular recipe in R. The zeros below R's diagonal are the visual signature of the fact that each original column only uses orthonormal directions discovered up to that point. Crooked equals clean times triangular. That's the whole story of QR in one image. Let's run it on two vectors in the plane. Take A1 equal to 3, 0, and A2 equal to 2, 2. Step 1, A1 has length 3, so Q1 is 1, 0, a unit vector pointing along the x-axis. Step 2, project A2 onto Q1. The dot product A2 with Q1 is 2. Subtract 2 times Q1 from A2, 2, 2 minus 2, 0 gives 0, 2. That's B2, and it has length 2, so Q2 is 0, 1. Now check our work. Is Q1 perpendicular to Q2? Their dot product is 0? Yes. Do both have length 1? Yes. So we produced an orthonormal basis, and in this case it came out as the standard x and y axes, which makes sense. A1 already lay along the x-axis, and stripping the x part out of A2 left it pointing straight up. A clean first run that shows every step of the machine working. Now a 3x3, so you see the full QR drop out. The three columns are 1, 1, 0, 1, 0, 1, and 0, 1, 1. Start with the first, its length is the square root of 2, so Q1 is 1 over root 2 times 1, 1, 0. For the second column, its dot with Q1 is 1 over root 2. Subtract that projection and you get 1/2, negative 1/2, 1, which normalizes to Q2 equal to 1 over root 6 times 1, negative 1, 2. For the third column, subtract its projections onto both Q1 and Q2. The remainder normalizes to Q3 equal to 1 over root 3 times negative 1, 1, 1. Now build R. Its diagonal entries are the lengths we divided by, root 2, root 3 halves, root 4 thirds, and the entries above the diagonal are exactly the dot products we computed along the way, like a 2.q1 equals 1 over root 2. Everything below the diagonal is 0. The bookkeeping we already did is the factorization. Whenever you compute a q, you should verify it, and the verification is just dot products. Take the 3 orthonormal vectors from the previous example. First check the diagonal, each vector dotted with itself should be 1. q1 with itself 1 plus 1 plus 0 over 2 equals 1. q2 with itself 1 plus 1 plus 4 over 6 equals 1. Good, both are unit length. Now the off-diagonal entries. Different vectors dotted together should be 0. q1 with q2 in the numerator 1 times 1 plus 1 times negative 1 plus 0, which is 0. q1 with q3, negative 1 plus 1 plus 0, also 0. Every pair gives 0 and every vector gives 1 with itself, which is exactly the statement that q transpose times q is the identity matrix. This check costs only a few multiplications and catches almost any slip in the Gram-Schmidt arithmetic. Always run it. A bit of history. Orthogonalization ideas float through the least squares work of Laplace and Cauchy in the early 1800s, but the process got its name later. In 1883, the Danish mathematician Jørgen Petersen Gram used orthogonalization while studying series and determinants. Then, in 1907, Erhard Schmidt, working on integral equations, wrote down the clean recursive version we still teach, subtract the projections, normalize the remainder, which is why we call it Gram-Schmidt. The factorization's biggest modern role came in 1961, when John Francis in England and Vera Kublanovskaya in the Soviet Union independently invented the QR algorithm for computing eigenvalues, repeatedly factoring a matrix and multiplying the pieces back in the opposite order. That algorithm is still, decades later, the method your software reaches for when you ask for eigenvalues. A 19th century trick grew into a pillar of numerical computing. Let's recap. The goal was to turn any basis into an orthonormal basis spanning the same space. The Gram-Schmidt process does it for each vector, subtract its projections onto all the directions already chosen, then normalize the remainder. Each step is just last episode's projection, keeping the perpendicular error. When you record the dot products as you go, they assemble into the QR factorization, A equals Q times R, where Q has orthonormal columns and R equal to Q transpose A is upper triangular. Q satisfies Q transpose Q equals the identity, so it preserves lengths and angles, of rigid motion. R has positive entries on its diagonal, the lengths of the leftover vectors, and being triangular, it makes solving systems easy. AX equals B becomes RX equals Q transpose B, finished by back substitution. This factorization drives least squares and the QR eigenvalue algorithm. Next episode, we use it to solve systems that have no exact solution at all, the method of least squares. Today we manufactured orthonormal bases and discovered a factorization. The Gram-Schmidt process takes any independent set of vectors and produces an orthonormal set spanning the same space. The rule is simple: keep the first vector and normalize it. For each later vector, subtract its projections onto all the directions you have already locked in, which removes every component pointing along them, and then normalize what is left. The leftover is perpendicular to everything before it, because subtracting a projection always leaves an error orthogonal to what you projected onto. When you record the bookkeeping, how much of each original vector pointed along each new direction, those numbers assemble into an upper triangular matrix R, and the orthonormal directions become the columns of a matrix Q. The result is the QR factorization, A equals Q times R, where Q has orthonormal columns and R is upper triangular with positive diagonal entries. Because Q transpose Q is the identity, problems that were tangled in the original basis become trivial in the Q basis. Next episode, we put this to work on least squares, where we solve systems that have no exact solution by projecting onto the column space. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.